Welcome to video 4.4 in our First Principles of Astrophotography series. In this video, we discuss the spectra of emission nebulae, which emit much of their light at discrete wavelengths.
This video and the two that follow explore the physical origins of the Sulfur-II, Oxygen-III, and Hydrogen-alpha emission lines that are targeted by narrowband astrophotography filters.
This video is based on section 4.4 of our First Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 57. Discrete spectra. Diffuse nebulae, planetary nebulae, and supernova remnants have discrete spectra.
So what do we mean by discrete spectra? This is what we mean. Here's a spectrum of the Orion Nebula provided by Richard Walker, who's the author of the Spectral Atlas for Amateur Astronomers. He's got spectra of a whole bunch of different objects. The Orion Nebula is one, and he sent me the data, which I've used to make this plot, because I wanted to overlay some other things. But just to give you an idea, we're talking about how much light is emitted on the vertical axis versus wavelength on the horizontal axis. And you can see that we're going from 400 nanometer wavelength to about 700 nanometer wavelength. There's a reason for that, and that is that, at least for us, our interest is in visible wavelengths. And most telescopes are designed for visible wavelengths so that they'll be perfectly in focus for all of the visible wavelengths. If you move into the ultraviolet or the infrared or the ultraviolet, you start to get where the optics aren't designed for those wavelengths, and you get blobby aberrations, blobby, ugly looking stuff. So we'll be talking in this video and in the next two videos about the hydrogen alpha line. This is a red line. We'll talk also, these right here are the hydrogen alpha, Sulfur-II, and Oxygen-III filters, the colored traces here. The black is the actual spectrum of the Orion Nebula. So this hydrogen alpha line is red in color. This Oxygen-III line is a blue-green.
You might say teal.
Blue-green, teal, turquoise. It's somewhere between blue and green in that spectrum there. And there are actually two oxygen lines, one at 500.7, which is stronger, which is normally targeted by Oxygen-III filters. There's also a weaker one at 495.9 nanometers, very close to it. This is the hydrogen beta line. We'll talk about that on the hydrogen gamma line, from the hydrogen bomber series. Right here is a little blip that there's hardly any energy in this Sulfur-II line. When you look at the Ring Nebula, you can see that there's a little bit more of a continuous background. For the Orion Nebula, the background is just pretty much zero, except at those particular lines.
It's nice.
Then at the Ring Nebula, you get some broadband, which you could capture with LRGB filters, right? And you get a little bit more sulfur here than you did with Orion. You still also get the hydrogen alpha, and you get a nitrogen line that we'll talk about also in the two videos that follow. Then for the Crab Nebula, it is a supernova remnant. So let me just point out, Orion Nebula is an emission nebula, is what we call it. The Ring Nebula is called a planetary nebula. It has nothing to do with planets. It's the remnants of a star that's pushed out its outer layers, leaving behind a little white dwarf in the center of the nebula. And the Crab Nebula is a supernova remnant. This supernova exploded in the year 1054 and was noted by Chinese astronomers, and it's been expanding ever since. We'll talk about the fact that it's expanding so fast causes these hydrogen alpha lines to split, one red shifted and one blue shifted, and which causes problems for super narrowband filters. You'll also see that there's quite a significant continuous background spectrum in addition to the emission wavelengths here, and that's caused by synchrotron radiation. We'll talk about that too. We're really, really proud of this image. This is an image that we took with our C-star, one of our proudest images, honestly, with our little darling C-star S50. And I don't know if you can see it in this video, but there's two lines, a vertical yellow and a horizontal yellow line, and they mark the position of the Crab pulsar, which we observed with the C-star. And we drizzled the bazookas out of that thing to try and get it. I think it was like 4-time drizzle or something, and processing and looking at it, etc. But yeah, it was a really proud image.
Principle 58, photon frequency. An electronic transition in an atom from an initial state with energy EI to a final state with lower energy EF emits a photon of frequency nu, and energy EI minus EF equals h nu.
So in a previous video, we talked about the photon energy being h nu, where h is Planck's constant. And that's the extremely small constant, 10 to the minus 34 joule seconds, that governs all of quantum mechanics. Here, the energy that's carried off by this photon, so this is the photon, and here's its energy, h nu. But what that energy is the differences in the energy levels of the electron as it moves from a higher energy state to a lower energy state in the atom. So you can think about it as like the different planets in orbit around the sun. The ones that are farther having, if they were all the same mass, the farther away, the more energy they would have. That's kind of the Bohr model, and it's not very accurate in terms of the physics because the electrons are really in clouds and it's complicated, but it gives you an idea that there can be higher energy orbits and lower energy orbits, and that's all we really need to know. And if you transition from a higher energy orbit to a lower energy orbit, the difference between those two energies is going to be the energy of the photon that's emitted. And that's where those spectral lines come from. Hydrogen alpha, beta, gamma, oxygen-2, nitrogen-2, and oxygen-3, nitrogen-2, and sulfur-II. Thanks so much for watching.
And we'll see you next time.